Chapter 12, Section 2, Distance-Based Clustering. In this section, I will explain the concept of distance and distance-based clustering. Clustering algorithms divide data points by their similarities. In distance-based clustering, similarities are measured based on the distance between data points. Specifically, nearly located data points are regarded as similar, and far-away data points are regarded as dissimilar. So, in distance-based clustering, while nearly located data points are grouped into the same cluster, far-away data points are grouped into different clusters. A distance-based clustering model optimizes the clustering by minimizing the distance within a cluster and maximizing the distances between clusters. For example, as depicted as these figures, we can cluster the same data in different ways. But as we can see, the lower plot achieved smaller within cluster distance and a larger between cluster distance. So, the lower plot is the better clustering. As a preparation for learning the concept of distance, let's recap basic math a little. Pythagorean theorem. It expresses the relation between three sides of the right triangle. Here is a right rectangle. Small a and b are legs, and small c is the hypotenuse. As expressed by this equation, according to Pythagorean theorem, the square of the length of the hypotenuse equals the sum of the squares of the lengths of the legs of the right triangle. There are various measures that quantify distance between data points. The most popular one is the Euclidean distance. Simply speaking, Euclidean distance is a linear distance. That is, the length of a straight line that connects the two data points. Euclidean distance can be computed by Pythagorean theorem. For example, let's compute the Euclidean distance between the point P and point Q. The point P's x-coordinate is P1 and its y-coordinate is P2. The point Q's x-coordinate is Q1 and its y-coordinate is Q2. If we connect the point P and Q by a straight line, we can create a right triangle. What we want to know is the distance between P and Q. That is, the length of the straight line, PQ. Since the straight line PQ is the hypotenuse of the right triangle, we can apply the Pythagorean theorem. So, the distance between P and Q can be computed by this equation. It is the Euclidean distance between P and Q. Let's look at a simple example. Suppose we have employee data, which contains data of work motivation and individual job performance. Both are evaluated by 5-point Likert scale. There are much more observations, but let's look at only these three employees. As we can see, employee A is high in both motivation and performance. Employee B is moderate in both motivation and performance. Employee C is high in motivation, but low in performance. In this case, which of B and C is more similar to employee A? We can solve this problem by computing the Euclidean distances. The Euclidean distance between A and B equals the square root of the sum of the squares of the difference in variables between the two data points. So, compute the sum of squares of the difference in motivation and that of performance, and then compute the square root of the sum. The distance equals 2.83. Similarly, we can compute the Euclidean distance between A and C. The distance equals 4.00. So, based on the Euclidean distance, we can say employee A and B is more similar than A and C. Let's look at another case. Suppose we have customer data, which records each customer's age and annual income. There are much more observations, but let's look at only these 3 customers. As we can see, these 3 customers are almost the same income level. But customer C is much older than A and B. So, intuitively, the similarity between A and B is higher than that between A and C. Let's compute the Euclidean distances. The result shows that, contrary to our intuition, B is more distant from A than C. That is, customer C is more similar to A than B. This counterintuitive result is due to the difference in data distributions. Age and income are different in unit, so the average value and variance are widely different. So, the absolute values of annual income are much larger than age. So, a slight difference in annual income has a large impact on the Euclidean distance. On the other hand, the age difference of 25 years has the same impact as income difference of only $25. However, the distances computed in this way do not reflect the actual similarity. To address this problem, we can use standardization. Standardization is a way of data transformation that makes the variable have a mean of 0 and a standard deviation of 1. It is done by this formula. We subtract a mean from observed value and then divide it by the standard deviation. The standardized value is called a z-score. A z-score has a mean of 0 and a standard deviation of 1. Using z-scores, we can compare variables with different units. Let's use the customer data as an example. We standardize age data for each customer. First, we compute the average and the standard deviation. Suppose when all customers included, the average age is 40 and the standard deviation is 10. Then, for customer A, subtract the mean age from age and divide it by the standard deviation. By doing so, we can get a standardized value. It is -1. Similarly, we can standardize B's age and C's age. Then, we can use the standardized scores for computing the Euclidean distances. As noted in the definition, if all observations are included, the average of standardized value is 0, and the standard deviation is 1. As an example, let's compute the Euclidean distances using standardized customer data. This is the original dataset, displaying only 3 cases. Suppose these are the mean and the standard deviation of each variable. Using these values, we can standardize the data. Now, let's compute the Euclidean distances between A and B using the standardized data. It is 0.36. Similarly, we can compute it between A and C. The result shows that the distance is smaller between A and B than A and C. That is, B is more similar to A than C. It may reflect the actual similarity. As we have seen, when we compute the Euclidean distance between variables with different units, it's better for us to use standardized data. Thank you for watching. Please thumbs up and subscribe to my channel.